In this video, we're going to be looking at our equations of motion graphically. We're going to be running out these situations that have several changes in motion. For each change in motion, we're going to have to make a variable list, so it's going to be convenient to just use a table like this. Then we're going to be graphing our displacement, velocity, and acceleration. We're going to graph all of those together so that we can see the relationships between those graphs. That relationship is what we would call in calculus a derivative and an integral. So let's get started. A car begins at rest and accelerates at 1 meter per second squared for 5 seconds. So this is our first situation. We are going to start from rest. That means our initial velocity is 0. We are starting, so we are at an initial position of 0 as well. Our time is going to be 5 seconds. And then our acceleration is going to be a positive 1. So what we want to know is what is the displacement? What's the displacement I take after those first 5 seconds? And then what is my velocity after those 5 seconds? Well, the velocity is very easy to find since it's just v equals v naught plus a t. And that v will be equal to 0 plus 1 times 5. So our final velocity for this part will be 5 meters per second. And then our displacement will be found using x equals x naught plus v naught t plus 1/2 a t squared. Well, x naught is 0, v naught is 0, so we're really just going to have x being equal to 1/2 of 1 times 5 squared, which will give us 12.5. Our second bit of motion will be the car traveling on a constant velocity for 10 seconds. And so our time here will equal 10. Our initial velocity here is going to be our final velocity from the last problem, so it'll be 5. And then our initial displacement here will be our final displacement for the last problem. And then we're traveling at a constant velocity, so our acceleration is 0. So this becomes pretty simple. Our final velocity here will be another 5 seconds. And then we just take 5 times 10, which gives us 50, plus 12.5. That gives us 62.5. And that's found because if the acceleration is 0, then this whole term becomes 0, and we just take our velocity times our time. So then our third piece of motion, what is this going to be? The car then slows at a rate of -1 meters per second squared for 5 seconds. So again, a time of 5, an acceleration of -1, and we use our previous final velocity for our new initial, and our previous final displacement for our new initial displacement. And so here, we're going to plug all of these variables into this same equation. So let's clear this. And we've got x being equal to 62.5 plus 5 times 5 plus 1/2 times -1 times 5 squared. And if we take all of that together, we end up with 75. And so our final displacement is 75. And then our final velocity, that would be v equals, and then it's going to be 5, it's our initial velocity, plus -1 times 5, which this is going to be 5 minus 5, so 0. So now that we have all of these variables, we can start putting these into the graphs. So let's start by making our acceleration graph. That's going to be the easiest one, and we'll do that in green. It's going to be acceleration versus time. We're going to have a midpoint of 0. We'll go down to -1. We'll go up to +1. For our first 5 seconds, we are at 1. And so this is 1, 2, 3, 4, 5. Put 5 there. So after our first 5 seconds, we go down to 0. And we stay at 0 for 10 seconds. And then we go down to -1. So then I've just connected my dots here, and I'm going to mark this middle line as 0. Because my velocity will then have the slope of its line being equal to my acceleration at each moment in time. So for the first 5 seconds, the velocity is going to have a slope of 1. For the next 10 seconds, it'll have a slope of 0. And for the last 5 seconds, it'll have a slope of -1. Let's do our velocity in blue. And our velocity goes from 0 to 5, so let's just track this as 1, 2, 3, 4, and 5. After the first 5 seconds, we've reached 5 meters per second. And we stay there until 15 seconds. And then at 20, we've slowed down to 0. And we started at 0. So let's connect those dots. Now, while the slope of the velocity versus time graph is acceleration, the area under this curve will be equal to my displacement. And that's going to be because if I take my base times my height, I'm taking velocity times time. And that's going to give me displacement every time. The only weird thing is that my velocity is changing here. So after 1 second, I would have traveled 1 times 1 times 0.5, 1/2 of that, because this is a triangle. I would have only traveled 0.5 meters. Let's use red for displacement. We've traveled 0.5 meters. After 2 seconds, well, now I've added another 1.5. So the total here would be 2. After 3 seconds, I would add to that 2, 1, 2.5. So this would now be 4.5. Then, again, after 4 seconds, I would add to that 4.5, 1, 2, 3.5. So I would now have 8. Then lastly, at 5 seconds, I'm going to add 1, 2, 3, 4.5 to that 8, giving me 12.5. So we can see that each moment in time, my displacement is not going up linearly. It is going to be going up exponentially more. If I have a slope for my velocity, then the area under this curve is getting bigger and bigger exponentially. And so I can track the displacement versus time up here, and we're going up to 75. So let's set 75 here, and then we'll go up by 15s. Yeah, 15, 30, 45, 60. And so after 5 seconds, after that first 5 seconds, we're going to be about 12.5. So we have not gone very far, but we are going to be sloping up to that. Let's do that a little better. So we slope up to that value. And then from the 5 seconds to the 15 seconds, we're going to go up to 62.5. And this is going to have a very steady curve. It's going to have a straight curve because this value down here, this area, when my velocity is staying steady, the area increases at an even pace. Every single second adds another 1, 2, 3, 4, 5 meters. So we can see this. Every second adds that same amount. So that means my slope for my displacement is going to be a very even slope. So let's set that up. And then for the last bit, I'm going in the opposite direction as my first 5 seconds. So for that last 5 seconds, from 15 seconds to 20 seconds, I'm going to be curving back to a steady slope. Because when I end at 0 for a velocity. That means I will have stopped. That means if I keep tracking beyond this, I will track a flat line. So I need to curve down to a flat line. And so there we go. There is our displacement graph. We've got displacement, velocity, and acceleration. Hopefully this helps us see a little bit better what these relationships really look like, what's really going on in these relationships. And so in the next assignment, you're going to be doing this same thing. You're going to be figuring out for each section of motion what your variable list looks like. Then you'll be constructing a set of graphs and showing the shapes and how they are related. Remember, the slope of your velocity graph will be equal to your acceleration at every given moment in time. The slope at 4 seconds is 1. The acceleration at 4 seconds is 1. The area under your curve in your velocity time graph will be equal to your actual displacement at any given moment in time. At 10 seconds, if I look at 10 seconds, I could say, hey, I've got the area of this triangle plus the area of this square. That's going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's 5 times 5, which is 25, plus the area under this, which is 5 times 5 divided by 2, which would be 12.5, so plus 12.5. And that would give me 37.5. Now if I come up at 10 seconds, I'm at about, would you look at that? That is right around 37.5. So that should track as well. That should track very nicely. So we need to be able to understand the relationships in these graphs. So go ahead and try these out and see if you can get these shapes right for yourself.